Hey guys, hope you all are doing alright on this splendid evening. Today we'll be giving a lecture on gauge symmetries. So this is a very, very important topic in quantum field theory. And it's a very exciting topic, and I'm very jubilant to talk about this topic today with you all. So, gauge symmetry. What is a gauge symmetry? So here's a brief rundown of what we are going to go over in this video. Some of the terms here might not seem clear as of right now, but by the end of this video, it will all make clear sense. So a gauge symmetry is when the Lagrangian is invariant under a gauge transformation. So we say that the Lagrangian has a gauge symmetry if it's the same under a gauge transformation. And a gauge transformation is a local field transformation. I'll go over what local means in this video. And a gauge field is the field in which the gauge transformation acts upon. So again, in this video, we'll be covering all three of these terms, plus some more cool stuff. So an important aside is that the gauge transform is technically speaking the local field transformation. So when a lot of people talk about gauge transformations, they usually mean only local field transformations. Now everyone has their own special definition of what a gauge field is, and that's what I've experienced. You'll see different definitions of a gauge field out there, but the most common one is that a gauge field is a field in which a gauge transform acts on, and a gauge transform will be defined as a local field transformation. But in our series, gauge transform is just any field transformation. So the reason why we are going to sort of make our definition more general is that it's just more intuitive, in my opinion, to define a gauge transform in that way. I'll always be clear whether I mean a local gauge or a global gauge. Now, if you don't know what local means, what I said might just seem like mumbo jumbo, but again, we're going to talk about what that means in this video. So, yeah, so for our purposes, a gauge transform is just any field transformation, both local and global. But when people talk about it, they might usually mean only local transformations. Okay. So an important video to watch is my video on the Maxwell equations, because we already had a taste of gauge theory from that video, because we actually used a gauge transformation to solve the Maxwell equations. So watch that video to gain some natural intuition on gauge theory and why it's useful. So the EM potential is a gauge field, and this was the focus on the last video on gauge theory. So I highly recommend watching that gauge theory video since we talked about the EM gauge. Alright, so watch those videos it's just good to watch those videos to gain some more intuition on the subject. And our core topic of this video is Noether's theorem for gauge symmetries. So Noether's theorem, a brief rundown, is that a symmetry implies a conservation law. Now, I made 2 videos on Noether's theorem already, and those focused on external transformations. Of all these videos I'm suggesting in today's video, Noether's theorem videos are the most important ones to watch. Because if you don't watch these ones, unless you already know Noether's theorem, you might have a hard time following along. So I highly stress that you watch the 2 videos on Noether's theorem, because that's what this video is going to be about. Noether's theorem for gauge transformations instead of external transformations. So it's all in the QFT playlist. So just click on that playlist, and you're going to see it there. So for Noether's theorem 1 and 2, we dealt with what are called external transformations. So external transformations is when we transform space-time itself. So for example, space translations and time translations are external transformations. We transform the background in which the fields exist upon, right? And we found out that for space transformations, we had momentum being conserved. For time translations, we had energy being conserved. But we can also consider internal transformations. And these are the very special ones in quantum field theory, where all the cool things happen. Because an internal transformation is when we change the field itself. So instead of changing the background space-time and our Lagrangian being invariant, we instead change the field itself. And that's called an internal transformation. So here's the free scalar field, and we're just changing the field by delta of phi. So internal transform is when we change the field itself. If that didn't make any sense, here's an example. So here's the Lagrangian for the free scalar field. You've seen it many times. You guys might have already memorized it by now. Here is an internal transformation. We have our field phi, and we scale it by a factor of 2. The multiplying by 2 is the internal transformation, since we change our field itself. We don't change x, we don't change t, we don't change space-time. All we change is our field itself. And by actually doing that, then plugging this in for phi, for like the new phi tilde in this case, we get this equation. We get this equation right over here. So of course our Lagrangian changed when we scaled our field by a factor of 2. So we would say that this Lagrangian is not invariant under the internal transformation by scaling the field by a factor of 2. So that's a nice example of an internal transformation. It's when we change the field itself. And whereas an external transformation is when we change the background space-time itself. So now that we have our background, let's now dive into the main lesson. So we can transform our field phi by some gauge transformation. Again, a gauge transformation is defined as being an internal transformation for our purposes. So we change phi to phi plus delta phi. So we're changing our field by some amount. This delta phi that you see here, they stacked on each other. This delta phi that you see here, it's called an infinitesimal change. So for Noether's theorem, just like our last videos on Noether's theorem, it's easier to work with infinitesimal transformations. And then at the end, we can plug in finite transformations to our field. So for now, we are going to deal with changing our field by an infinitesimal amount. So this means that partial mu phi is going to change as well to partial mu phi plus partial mu of delta phi. So same thing for the partial mu phi. Under that gauge transformation, it is also going to change as well. And our Lagrangian, in general, will change to L plus delta L. Or again, delta L is the infinitesimal change. So our Lagrangian in general will change if we change our field. Now, if our Lagrangian is symmetrical under the transformation, so if we have a gauge symmetry, this means that L is going to equal L plus delta L, since it won't change under that gauge transformation, which implies that delta L equals 0. So for a gauge symmetry, delta L is going to be 0. And this is the equation that we are going to work with throughout this video. So what is the formula for delta L? Well, our Lagrangian, first of all, we should write it out for the free scalar field case. But this is just one example. What we say here will generalize to all kinds of fields. For the free scalar field, our Lagrangian will depend on phi and partial mu phi, right? Since it is equal to 1/2 partial mu phi plus m squared phi. So all we have to do is consider the functions on phi and partial mu phi for our Lagrangian. So if our Lagrangian depends on phi and the derivative of phi, this means that delta of L is going to equal partial L over partial phi, delta phi, plus partial L over partial of partial mu phi, delta of partial mu phi. So all we've done here is multivariable chain rule. So if you're watching a video on quantum field theory, I'm going to assume that you already know multivariable chain rule. If you don't know it, I made a video on it in my tensor calculus series. So just check that video out if you're unfamiliar or rusty with the multivariable chain rule. So what we have to do now is we can notice this term over here, this partial L over partial phi term. We know that from the Euler-Lagrange equations that partial mu of partial L over partial of partial mu phi is going to be equal to partial L over partial phi. These are the Euler-Lagrange equations. So here we have this partial mu phi term. So we can just plug in this term for partial L over partial phi. And this is going to give us delta L equals partial mu of partial L over partial mu phi, delta phi, plus partial L. You should move this to the left a bit since we are running out of space. Partial L over partial mu phi, delta of partial mu phi. We can then move the partial derivative in front of our delta to get that delta L equals partial mu of partial L over partial mu phi, delta phi, plus partial L over partial of partial mu phi, partial mu of delta L of delta phi. So all we've done here is we've just moved the partial derivative in front of our delta phi. What we can now do is factor out the partial derivative in front here. We can see that delta L equals partial mu of delta L over partial mu phi times delta phi. And we can do this because this is just the product rule. The derivative of this times this is going to be the derivative of the Lagrangian term times the delta phi plus the derivative of delta phi times the Lagrangian term. So we are able to condense it into one simple equation. And remember, if you have a gauge symmetry, delta L is 0, right? This means that partial mu of partial L over partial mu phi, delta phi, is going to be equal to 0. And we're pretty much done here. We've derived a continuity equation. We can define this term in the middle to be some quantity called, let's say, q mu. Then we have partial mu, q mu, is equal to 0. And this is a continuity equation. And like we've said in our other videos on Noether's theorem, if we have a continuity equation, we should pay extra close special attention since it usually tells us that something in our system is being conserved. What we can actually do here is we can expand partial mu q mu. We can expand that out to get partial naught q naught minus partial I q I equals 0. This is completely analogous to what we did for the first two videos of Noether's theorem, or technically speaking, the last of the first two videos of Noether's theorem. So this is just partial t of q naught, since partial naught is defined as partial t, the time derivative, minus partial I q I equals 0. We can then just add both sides by the I part to get this over here. We can then just take the integral over the three-dimensional volume element on both sides. Again, same thing that we did for the other video. Then we can notice that this is just the definition of the divergence of the three vector q. So integral of the volume element partial t of q naught equals the integral 3 volume element of the divergence of q. Now there is a property from vector calculus that says that this is going to be equal to 0. And we talked about that in the second video on Noether's theorem. The divergence of a vector field integrated over the volume element is going to be equal to 0. So now we have that integral of the volume element partial t q naught equals 0. We can move the partial t to the front to get partial t integral of volume element q naught equals 0. And this is actually our conservation law, since we have the time derivative of some quantity equals 0. So the quantity integral of q naught is our conserved quantity. This is our conserved quantity under gauge transformation, so field transformations. And that's our conserved quantity. So let's actually use some specific examples now. So let's just write out what q naught will be for convenience. So we found that q mu is this inner term over here, right? So let's just copy that. Let's paste it. So this was q mu, meaning that q naught is going to be equal to the same thing, but now we have partial naught phi. So if we integrate this term, that's going to be our conserved quantity. Let's now actually consider what are called field shifts, where the transformation is we take our field and we shift it by some value I omega, where I is the imaginary number and omega is some real number. So this is called a field shift, by the way. So what's our conserved quantity under field shifts? Well, remember that we first did phi to phi plus delta phi. So the minus I omega plays the part of the delta phi. So our conserved quantity in this case is just going to be equal to partial L over partial naught phi times minus I omega. So here's our conserved quantity under field shifts. And this is so simple. We can just consider a bunch of different gauge transformations, and all we have to do to find the conserved quantity is we just plug in what delta phi would have to be for our case. So all we do here is we just plug in minus I epsilon to substitute the delta phi to get that finite transformation. And we get this q naught quantity being conserved. So this means that the integral over the volume of partial L over partial naught phi times minus I omega is going to be equal to 0. We can then just move this minus I omega to the front since it's a constant, and then divide both sides by minus I omega, and we'd get that the integral of the volume element partial L over partial naught phi equals 0. So it turns out that this is also a conserved quantity. Conserved quantity. Let's call it like, I don't know. Let's call it K. So conserved quantity K. K for conserved. So what we found here is that under a field shift, if our Lagrangian, that's the big part, if our Lagrangian is invariant under those field shifts, that means that this quantity K, not just Q naught, but K will also be conserved, since we could just factor out that field shift to the front, and then divide both sides by that field shift. So this quantity is also conserved. All right. Now, a pretty interesting thing is, well, what is this value equal to? And we can actually find out what partial L over blah 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 is equal to. So our Lagrangian is equal to 1/2 partial mu phi plus m squared phi squared, right? So we want to find partial L over partial naught phi. So that's just partial over partial naught phi of 1/2 times, we can expand this partial mu phi term to partial naught phi minus partial I phi plus m squared phi squared. Okay, so when this derivative actually goes inside the term here, all of these terms are going to go to 0 since they don't have that partial naught phi term. So this is basically partial naught phi but squared, and the derivative of that is just 2 times partial naught phi. This 2 will cross cancel out with this 1/2 over here, and we will just get that partial L over partial naught phi equals partial naught phi, since that's what remains. Actually, this should be an underscore naught. So this is the actual value for the conserved quantity, or once integrated over the volume, right? And what's really cool about this quantity is we can interpret this in a nice way. Now, we can't really interpret it in like how would I say this? This quantity isn't like momentum or energy or anything like that. It's more of an abstract thing, but we can still interpret this. Partial naught phi, all it is the time derivative of phi. So essentially, the rate of change of our field over time is what's being conserved. If we have a field shift symmetry of our Lagrangian. So basically what we're saying here is that this thing over here is just equal to partial naught phi. And we have simplified our equation a huge ton. Now the actual elephant in the room question is our Lagrangian actually invariant under field shifts? Well, let's check. Remember that our field shift is it's phi to phi minus I epsilon. And our Lagrangian is 1/2 times partial mu phi plus m squared phi. So L tilde, the new Lagrangian, is going to be partial mu of phi minus I epsilon, partial mu of phi minus I epsilon, plus m squared phi minus I epsilon. And this is going to equal 1/2 times partial mu phi partial mu phi, since this derivative is going to be 0 once we validate it with this constant term, right? So we have partial mu phi plus m squared. This should be a phi squared, by the way. Did I not write phi squared for our Lagrangian so far? Yeah, we did. This should be a phi squared. So we had a m squared times phi minus I omega squared. We have that this is 1/2 partial mu phi. Yeah, 1/2 the whole thing. Partial mu phi plus m squared times phi squared. So what's minus I epsilon squared? I'm just doing mental math here. It's late at night, but I believe that this should be plus omega squared, and then minus 2I omega phi. If this plus omega squared isn't completely correct, I mean, well, sue me. So this is the term over here. And of course, this Lagrangian isn't invariant, because look, while this term is good so far, the mass term messes everything up, right? We're getting extra terms with omega and 2I and ugly and nasty, ugly things. So our Lagrangian isn't invariant. L isn't invariant under field shifts, which means that partial not phi is not a conserved quantity, or related to a conserved quantity. And you might think, this is a big problem. We just destroyed physics, but we really haven't here. Since even in classical physics, there are still Lagrangians that don't have symmetries that lead to some particular conserved quantities. Should have rephrased that, but you'll see what I mean here. For example, the Lagrangian for a particle that's like falling down under a gravitational field is 1/2 mv squared minus mgx, okay? If we change x like x minus a, Lagrangian is now 1/2 mv squared minus mg times x minus a. So this corresponds to moving our coordinate system to the right by the value a. So now we have 1/2 mv squared minus mgx plus mga. So our Lagrangian, our new Lagrangian, just gained an extra constant term. So our Lagrangian for gravity isn't invariant under that space translation. That's what it's called. Meaning that momentum isn't conserved. And no kidding, Sherlock. Of course momentum isn't conserved. If you drop a stationary ball from the sky, it starts to accelerate. So momentum obviously is not conserved. That's not a big problem, as long as we realize that, hey, our system isn't actually closed. If we considered the Earth and some planets, and then you consider the Lagrangian describing both systems, well, the Earth Sun system, this should have been the Sun, this is the Earth, then we have a conserved quantity. Then momentum is conserved. But for just the Earth itself, since the system is open, our Lagrangian won't be invariant under that transformation. Not the exact same thing in this case, but I'm saying this so you guys aren't like confused. The Lagrangian won't always be invariant under certain things. So in this case, our Lagrangian is not invariant under that field shift. This does not mean that partial not phi is not a useful quantity. Momentum is still useful, even though it's not conserved for a falling apple. And it turns out that this partial not phi is very useful in QFT. In fact, one could argue that it's like the top 2 most useful things, because we actually use this in second quantization. So we like to define partial not phi as some quantity called pi. We call this the momentum, the field momentum conjugate. And we use the symbol pi to represent that. this pi isn't the same pi. It's not the same 3.14159 blah 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 pi. It's just a symbol pi, and this quantity we actually use it in second quantization. We say that phi, the commutator phi and partial not phi, or better said phi and pi, equals like this thing over here. And this is how we actually derive quantum field theory. So partial not phi is a very important quantity that we will be using a lot in the future. So don't think that it's useless. It's useless just because it's not a conserved quantity. Now, something that you guys may have noticed is that if mass is 0, if you have a massless field, so like massless Higgs bosons, massless pions, if m equals 0, then this entire term just goes away, right? It poofs, our problems fade away, right? And this term will go away, and our Lagrangian is now gauge symmetry invariant. We now have a gauge symmetry, right? Since our Lagrangian would just be this guy over here. And it now is invariant under that gauge transformation. So if mass is 0, invariant, so we have a conserved quantity, bingo, we're all happy. But if mass is non-zero, so if mass is 0, we have a gauge symmetry. But if mass is not equal to 0, no more symmetry for us. So it's like mass just ruins everything in physics. Mass, we say that mass breaks the symmetry. Mass breaks the symmetry. Since we once had a symmetry, now we don't have it anymore because mass is a thing. Too bad, so sad, right? And it turns out that this mass symmetry breaking is what sort of leads to the Higgs mechanism. But that's a story for next time. But this whole mass thing is a very important part of physics. And we can use it to explain how mass comes about in the first place. So, yeah. Now, what if we do have mass equals 0, but instead we say that phi is transformed to phi minus I epsilon of x. So say we want our epsilon to change depending on space. This corresponds to saying that our entire field just doesn't move together. The epsilon value will change, or how much it shifted will change depending on the location. Is our Lagrangian still invariant even when mass is 0? Let's see. So our Lagrangian is going to be 1/2 partial mu phi times plus partial mu of minus I omega plus same thing, partial mu phi plus partial mu minus I. Did I say omega? I mean epsilon. And these epsilon should have of x next to it. Of x mu, actually. We want of x mu. So let's just do some cleaning up. Clean up crew. Phi plus partial mu of phi minus I. I keep saying omega, I don't know why. Epsilon. Okay, so if we actually carry out this derivative, what we're going to get is partial mu phi plus partial mu minus I epsilon of mu plus partial mu phi plus partial mu minus I epsilon of x mu, where x mu is some space-time point. So Lagrangian, of course, is still not invariant. Yeah, and it should be multiplied, by the way. So these are multiplied by each other. So this times this, if that makes sense. I'll try to clear it up a bit. But we'd have equal 1/2 times this times this. So this is of course not invariant anymore, because we can't just say, because before we could just say that these are just 0 since epsilon was a constant, but now that's going to depend on the space-time position. Is it going to have a non-zero derivative? So that just sort of sucks for us. And even if mass is 0, us having a gauge transformation that depends on space will eliminate the symmetry that we had. And this is actually a big problem in quotes for physics, because we actually call these local internal transformations. We call them local because, well, they depend on space-time. That's local, the place, right? So they're local. It's a local transformation because the transformation depends on the space-time point. And this is where the whole gauge thing comes from. A lot of people define a gauge transformation as only local internal transformation. So here is a gauge transformation. Like, pretty much everyone's going to agree that it's a gauge transformation. But for our series, again, we aren't going to be so strict on our definition. We are also going to consider global transformations. And global transformations are the opposites of local ones. Global ones don't depend explicitly on the space-time position. So, local internal transformation breaks the symmetry as well. We don't only need mass to break it. This thing can break it as well. In fact, it breaks it more effectively than mass. And it turns out that for the standard model of particle physics, we want local transformations. We want local gauge symmetries. So we want our Lagrangian to be symmetrical under local transformations. So, and a nice example is in quantum chromodynamics. We want our Lagrangian to be invariant under what's called an SU3 local transformation. And it turns out that if we do that, it's not invariant. So we have to add like extra terms to make it invariant to sort of fix that gauge in a way. And those extra terms end up being the gluon. So that just describes how the gluon comes about. But that's for the future, far in the future. But that's just an example of the uses of local transformations. So, yeah, that's pretty much it. So there are other transformations that we can talk about. We talked about field shifts, but another important big one is the U1 symmetry. This is a very huge symmetry, and that's the topic of our next video. There's also the SU2 symmetry. There's also the SU3 local symmetry that we just talked about briefly, very briefly. We will talk about all those good guys in the future, but U1 symmetry is for the next video on this playlist thingamajig. So, yeah, that's gauge symmetries, and that's that. I'm not really sure how to conclude this video. Thanks for watching, and subscribe if you're awesome, or don't if you don't want to. That's fine as well. Yeah, thanks for watching, and have a nice day. See you guys another time. Bye.